a simple random sample of 200 voters. They asked them whether we were voting for a new bond act. 110 of those surveyed said they planned to vote yes. What is the margin of error for this poll? Okay, so let's think about this for a second. What percentage of voters say that they're going to vote yes in this survey? 110 out of 200, right? Right, which is 60%, right? Or 55%. So P, I'm going to call it. I usually refer to the true population proportion as P. And very often when we're working with a sample, we're talk about the sample proportion as being Pcap, kind of like we use X bar. This is another kind of point estimate, right? So 110 out of 200 is going to be 0.55, right? So Pcap is equal to 0.55. So now we want to know how likely it is that what is the range within which we would expect to capture the true proportion of the population, of this population that's actually voting yes. So we're going to use this to determine the variability of the sample. And if you think about it, if a sample has depending on the proportion of the population that voted yes, that would suggest how variable any particular sample would be. If it were 10%, it'd be a bit more variable than if it were 40%, and 50% is probably the one that is probably the least variable, or the most variable, actually. So what we're going to do is I kind of reversed it there. We're actually going to calculate this. So what's our variability? What's our standard error for this going to be equal to? Our standard error is going to be equal to the square root of P times 1 minus P over the sample size. Okay, so what's our standard error? Our standard error is the square root of going to be 0.55 times 0.45 over the sample size, 1,000. So what would be the most variable outcome here?
The sample size 200.
I'm sorry, 200. Yeah, my brain, between the Dayquil and the cold, my brain is kind of fried. So 0.55 times 0.45. Well, let me ask you this. Let's say that that Pcap had been 0.1. What would we have on the top of this square root? We'd have 0.1 times 0.9. Right? Now, how does that compare to 0.5 times 0.5? Which one gives us a bigger product? Right? That one does. Right? 0.5 times 0.5 is 0.25. 0.1 times 0.9 is 0.09. So the closer you get to 50-50, the larger this number is going to be. So given the same sample size, the closer to 50-50 that you get, the larger standard error that you're going to have. That's just an aside, but let's take a look at how this affects us. So the standard error is going to be equal to the square root of 0.55 times 0.45. .55 times 0.45 divided by the sample size, which is 200. Got it right this time, which is equal to that number. And I'm going to take the square root of that number. That number is going to get bigger or smaller when I take the square root. It's going to get bigger, right? Because with decimals, when you multiply them together, you get a smaller number. So if I'm looking for the number which will multiply together will give you this one. So we're going to start with a bigger number. So take the square root, and it's going to be 0.035. So the standard error is equal to 0.035. So now what's our 95% confidence interval for the true value of Pcap? Right? It's going to be equal to Pcap plus or minus 1.96 times my standard error. So it's going to be equal to 0.55 times plus or minus 1.96 times 0.035 I'm gonna actually just double that. So I'm gonna call that 7%, right? 0.07, just to make it a little bit easier. So our confidence interval is going to be 0.48 to 0.62. So we're 95% certain that the true proportion of the population is between, going down pretty low there, right? Is between 0.48 and 0.62. Now, if I had asked you, we're 95% sure the true population is between those two numbers, right? Are we 95% certain that this proposition is going to pass? Are we 95% certain that the result is different than 50%? We're not, right? Because 50% could be the actual population mean. If instead our standard error was smaller and we wound up with a confidence interval of 0.51 to 0.58, right? We're 95% sure the true proportion is between those two. That means we're also 95% sure it's not 0.5. We can compare it to a single known value, a set value, 0.5. Things get a little complicated when we take two groups and compare them because they each have their own proportion and standard error and so forth. So then we have to make all sorts of other decisions. But we can start to see now that we can use this idea of our understanding of how samples perform with numerical variables. We can start to see that we can apply that to make judgments about whether or not a result from a sample suggests that a population is different than a set number, or say different from another population's value for the mean. So we're starting to see the beginnings of how we might use this when we apply it to real life and real studies and so on. And as we go through this, next week we're going to start to get into hypothesis testing. And in hypothesis testing, we're actually going to talk about this idea of what's the probability that these two populations meet, the sample from this population, sample from this population, these are the means. What's the probability that we can say that they're really different and that the differences are not due to chance? If you can imagine, if you don't know this about the variability, if you don't understand this, then what happens is if you take a mean from group A and a mean from group B, if you don't know what the probabilities are that they could be from the same population, well, then you'll never be able to make a judgment because even if they're from the same population, if you took two samples, you're going to get two different values, right? In other words, if I sampled 100 people from from population A and got a mean of 100, and I sampled population A again, I'm going to get a different mean. So if you consider, well, when I sample population A and population B, well, how do I know that I'm not really sampling two populations that really have the same mean, and the difference was just the same thing as if I had taken samples from that single population and they just came off different by chance. So that's really what's important to us here. That's really what we're starting to learn about here. So let me